Francisco, lá da Universidade Federal de Campina Grande. E eu tenho aqui uma colinha, né? Para me referir aqui ao nosso palestrante. Então, vou fazer um mix aqui de idiomas por causa disso, né? Então, it's an honor to receive Professor Francesco Petruccione, that his PhD in physics by the University of Freiburg, and has a second PhD, the habilitation by the same university. He has research in developing novel algorithms that harness the power of quantum mechanics to enhance the capabilities of traditional supervised learning methods. Dr. Petruccione has been published in numerous high-impact journals, and he has been a pivotal figure in several groundbreaking projects exploring the potential of quantum algorithms to outperform their classical counterparts. His recent research includes the development of quantum-enhanced support vector machines and their application in real-world data classification problems. In today's talk, Dr. Petruccione will delve into the fundamental principles of supervised learning, outline the challenges faced in the classical domain, and illustrating how quantum computing can provide innovative solutions. With his insights and expertise, we are sure to gain valuable perspectives on the future of artificial intelligence and in the realm of quantum technology. Please, Dr. Francesco Petruccione, come to our presentation. By the way, you have 15 minutes about that and 10 minutes after for the questions.
Perfect. Thank you very much. Thank you very much. So, bon dia. That's as much as I can go. So thank you very much for the very kind introduction. Thank you very much. It never happened to me before to be introduced but by name, Saint. So that's really something special. Yeah? And thank you very much to the organizers for having me here. And I apologize because I'm one of those horrible invited speakers that are very slow in replying to emails, but I'm here and I'm very happy to be here. So I'm not sure if we can we get it a little bit sharper? And how do I change the slides? Okay, so it will be very busy. Can we have the next one? Okay. Okay, so I'm based in Stellenbosch, which is at the southern tip of South Africa. So is there not? Don't you have a gadget to? No. Okay. And this is a photo of our campus. And some of the building, the nicest building is theology, so not physics. We are not in there. That's the theology faculty. Please, the next one. And I also wanted to maybe briefly mention my latest affiliation, which is the National Institute for Theoretical and Computational Sciences, which is based in Stellenbosch, and which is essentially a consortium of all universities in South Africa, but the headquarters are in Stellenbosch. And it's a really interesting institute because it brings together essentially all the basic sciences, including quantitative finance and a few other things. So it's a really crazy institute to direct, because all these communities didn't really work together before, and the aim is to force them to work together. Yeah? And I tell them every day that NITEC is an undisciplinary institute. You know, disciplines don't matter anymore. What matters is the solution of problems. So that's what we're trying to do. Ah, wonderful. That makes it much easier. Thank you very much. Okay, so what will we discuss today? I will, since this is a workshop and school, I will do a little bit of a mix of workshop and school. Yeah? But essentially, I will share maybe some thoughts about quantum machine learning in general, in particular, and maybe quantum computing in general. Yeah? So I don't know how it is in Brazil, but in South Africa, everybody speaks about the fourth industrial revolution. You can't hear it anymore. Yeah? And the reason why we are now in the fourth, sorry, I wanted to go back. Why we are in the fourth one is essentially Moore's law. Yeah? The exponential increase in computing capability with enormous numbers of transistors on chips. Yeah? And this image here on the left is the original plot from Gordon Moore, where he sort of extrapolated the law. Yeah? And it's still going strong. Yeah? Of course, this implies that there is also an exponential growth in computational power, yeah? In floating point operation. Yeah? This also doesn't seem to end this trend. Yeah? So I'm speaking classical computers here. Yeah? And of course, there is the inverse exponential decrease in costs. Yeah? You see, memories, hard drives, and so on and so forth decreases, the cost decreases following an exponential law as well. Yeah? What is also scary is that if we now slowly move towards AI, yeah, the amount of computational power needed to do the fancy ChatGPT things that we have in our pocket these days. Yeah, this is also an exponential increase in in computational resources. Yeah? What makes it scary, yeah, is the electricity consumption of the AI. Yeah? Because if you see, sorry, the resolution is not so nice here, but you see all data centers that do AI, yeah, consume more electricity than most countries in the world. Yeah? There's only the US and China that are more or less in the same order of magnitude. It was the OpenAI's, Google's, and Microsoft burn every day at electricity. Yeah? And I don't think it's really sustainable. Yeah? It's really very impressive. Yeah? Okay, so let me skip a few things. This is something that it should be interesting to the Brazilian community as it is to the South African community, and we're all part of BRICS. Yeah? Is that if you look at the statistics of the market share, yeah, for production, for instance, of chips that are used for CPUs and GPUs, yeah, neither South Africa nor Brazil is anywhere to be seen on these plots. Yeah? So we really need to do something to change that. So what is the way forward? You know, we are here, this is a quantum computing conference. Yeah? So classically, we use our bits, which is essentially mathematics plus information. Yeah? People that believe in kind of neuromorphic computing, like the biology plus information. Now we are here the physics plus information community. Yeah? So we need to see how these qubit quantum systems can help us accelerate scientific discovery and various other aspects. Yeah? This all started long ago. Yeah? Many of you are physicists. In the 80s, Feynman had this vision, yeah, that the microscopic world is quantum, so the best way of simulating it will be using some quantum kind of devices. Yeah? And in parallel to the industrial, thank you very much, that's very kind of you. In parallel to the industrial revolution, we have also the quantum revolution. Of course, it started more than 100 years ago with Einstein and Heisenberg and Schrödinger and company. Yeah. But in the 80s, people now define it as the beginning of the second quantum revolution, which essentially coincides with our technological ability of manipulating single quantum objects. Yeah? Until the 80s, we couldn't trap an ion, we couldn't do cold atoms, we couldn't do all those kind of things. Yeah? You know, the hydrogen atom in the quantum mechanics textbooks was just an idea. Yeah? Nobody had ever seen it or played with it singularly. Yeah? And the hope is now that to achieve the famous goals of the fourth industrial revolution, we really need to make use also of the second quantum revolution. Yeah? The first quantum revolution gave us very useful things, the transistors, lasers, diodes, the phones in our pockets wouldn't work without all these fancy things. Yeah? And now we are experiencing we experience the merging of two fundamental theories of the last century, yeah? Information science and quantum mechanics. They're just now a kind of a new science, yeah? Quantum information science, yeah? with three major building blocks, yeah? Computing, communication, and metrology and sensing, and of course, putting all together, the vision is one day to have a quantum internet of sorts. Yeah. The nice thing of these three blocks is that metrology will give us access to really interesting new data, yeah, that we never had before. Yeah? Without quantum metrology, we wouldn't know about gravitational waves, for instance. Quantum communication gives us the secure transport of the data, and quantum computing promises to give us the fast processing of data that we need. Yeah? And it is interesting, you know, computing and AI always went hand in hand. Yeah? You know, without the advent of GPUs, we wouldn't have the large language models that we have today, I guess. Yeah? And the question is, what will the QPUs allow us to do? Yeah? This slide is very important because you see I put, these guys here put quantum devices in this array between ASICs, FPGAs, and GPUs, yeah, which means that the worst case scenario for quantum computers is that there will be just a specialized processor to do something. Yeah? For instance, we know already that quantum devices are good at calculating kernels that you can use for AI and so on and so forth. Yeah? So the worst case scenario is already realized, yeah? Because we know we can use already specialized tools to do specialized calculations. Yeah? The dream is to have the famous QPU that solves all the problems of the world. Yeah? So, where are we? Yeah? And if you look here, this plot that is stolen from this recent paper, this review article on noise intermediate state quantum computers, and look at the number of qubits and the gate precision and the time, yeah? We are probably somewhere here, yeah, somewhere here, yeah, because the hope is to reach the era where we really have lots of logical qubits, yeah, that allow us to do error correction, improved quantum computations. Yeah? Where we are now in this NISQ era, yeah, is where we are trying to explore what we can really do now. Yeah? Because I think the time of the big promises is over. Now people expect that we start delivering something. Yeah? And this is very good because it shows us also already the limits of some of the algorithms that we were very hopeful to use for that purpose. Yeah? At the moment, I think this was data from a few months ago. Yeah, we have, let's say, order of magnitude 1,000 qubits is what we have available on various platforms. This is just a very simple table. Yeah, we have the superconducting technology, which has advantages probably, but also the very big challenge that you really need extreme temperatures, which make it quite difficult to scale it up. Yeah? Trapped ions is another very promising technology, but it's not so easy to scale, apparently. Yeah? Topological computers, and I've just met someone who works on topological quantum computing, are very promising, yeah? Because they have the really great advantage that they essentially operate like transistors. Applying a voltage, you can go from 0 to 1, which all the others can't do. So it really reduces the amount of electronics, of microwaves, enormously. The only problem is that we don't have that. Yeah, Microsoft claims to have one. Yeah, but that's it. Yeah. But anyway, we will see. Then there are photonic computers, yeah, that also have. Sorry, here's a spelling mistake. Advantages because photons don't interact so much. Yeah, but again, they also have challenges if you want to use something non-linear in the system. Yeah? So which technology will win? I don't know. I don't know, and your bet is as good as mine. I know that in South Africa, where we have since 4 or 5 years also a quantum technology roadmap, yeah? We decided explicitly not to develop our own quantum computer for now, because it will eat up all resources to do anything else. Yeah? And you risk that you put your eggs in the wrong basket. Yeah? So I don't know if you have a plan to build your own. I don't know. That would be interesting to discuss later. At some stage we will have to, of course, but at the moment it was just too risky. Yeah? On this slide, I just tried to summarize briefly all we have in quantum computing, all the algorithms that we have. You know, we started with the big developments in the 90s, yeah? With the famous Deutsch and Deutsch-Josse algorithm, yeah, that were the first algorithm to show some kind of advantage for a toy model. And then the big discoveries of Peter Shor, Grover, and so on and so forth that really kick-started the development. You know, once Shor showed the factoring algorithm, and in the same year, I think also the first way of doing error correction, yeah? That really kick-started the whole development of quantum computing, yeah? Because you know that you could do something useful and you could also improve the hardware with error correction. Yeah? And then, of course, there's a whole avalanche of many other algorithms. Yeah? When I teach quantum computing, yeah, I try to build it up from kind of quantum algorithmic primitives, yeah, that you can then put together to do other things. Yeah? And some of the really important ones are the quantum version of the Fourier transform, yeah? the search algorithm, of course, the Hamiltonian simulation, which was the original inspiration for building quantum computers, linear algebra, yeah? That is relevant for quantum machine learning, and for hybrid architectures, variational quantum algorithms were thought to be very useful for a long time. Yeah. All these building blocks, you can put them together. This is just an example. Yeah? You can use them to put them together to do more interesting things. So that is it's not just a big box. There are many Lego elements in the box that you can put together and try to develop something new. So let's skip this. The reason why people are excited about quantum algorithms is, of course, the quantum speed up. Yeah? And here you see a comparison for some typical algorithms, Grover, Shor, Fourier transform, eigenvalue solvers, yeah? And the comparison on how they scale with increasing system size n, yeah? And you see that on the quantum algorithm side, there are lots of square roots and logs, yeah? And that is good. Yeah? The more logs there are, the better. Yeah? That means that that's where really the exponential speed up is. That we really need, yeah, and I will show you at the end why we really need that. And in quantum machine learning, it's the same. Yeah? If you compare the classical and quantum version of the standard quantum machine learning algorithms, yeah, you see again on the quantum side there are lots of logs, yeah, and that is very good. That means that in principle there is an exponential. There's an exponential speed up in doing the quantum version of the machine learning algorithm. Yep. 5 years ago, there were lots of emotion and commotion because Google claimed to have reached quantum supremacy. Yeah? You all saw this title page of Nature, and you all saw the famous plots where they claim that what a classical computer could do in 10,000 of years, they could do in 200 seconds. Yeah? For a problem that is not really something that you use every day. Yeah, quite an artificial problem. But, you know, it didn't took very long, but already after a few months, people claim to be able to do it more or less much faster on classical computers. And just a few months ago, this Chinese group managed to solve the same problem with GPUs in a similar amount of time. Yeah? So the competition is working very hard. Yeah? I mean, they use 1,000 GPUs, yeah? But that means that with standard technology, you can reach exactly what Google claimed to have reached and claim quantum supremacy. Yeah? So it's very difficult to beat classical computers at this moment. Yeah? One also very recent paper from Quantinuum is that they show that they have now the ability using trapped ion technology to build roughly 50 logical qubits. Yeah? That's really sensational, yeah? Because you know all the other superconducting computers, they have maybe more qubits, but they're not logical. They're just physical qubits with error correction, without error correction, and so on and so forth. Yeah. So there's really hope that things are starting to move fast, even on the hardware side of things. Yeah? So this was, you know, just kind of stream of consciousness. Collection of thoughts about quantum computing in general. Yeah, let's move now to, let me check, okay, I still have some time, about quantum machine learning. Yeah? You know, quantum machine learning, and you all have seen these famous pictures, yeah? You can classify whether the data are classical or quantum, and your algorithms are classical or quantum. And typically, you know, if we want to show advantage on classical computers, we are concerned with this block where the data are classical and the algorithms are quantum. So there are fundamental differences in doing classical and quantum machine learning. Yeah? A classical machine learning algorithm, you have your data set, you have your kind of machine learning algorithm, and you make some kind of prediction. Yeah? For a quantum machine learning algorithm, you have, of course, the same data set and hopefully the same or even a better prediction. Yeah? But the block in the middle is completely different. Yeah? Because of how quantum systems work, we need to prepare a quantum state, we need to invent the Schrödinger equation for the quantum state, and we need to measure it. Yeah? So that means that there are essentially two additional blocks. Yeah? There is a block where we need to convert the classical data into quantum data, if you want. Yeah, then of course we need some quantum machine learning algorithm. Then we need to read out the quantum data. and do the classical prediction. And I will show you later that the stumbling block is this one here. Yeah, this I showed you already. You can reach exponential speedups for various algorithms. Yeah, but this block and this block are the very slow parts. That risk to make quantum machine learning not useful unless some of the young people here come up with something very interesting. Yeah? And it's definitely possible. Yeah? On this, in quantum machine learning, at the moment, yeah, variational quantum algorithms are very prominent. Yeah? But, and you all know how they work. Yeah? The idea is that you have a quantum algorithm that is parameterized. You do your state preparation, you process something, you measure, and you try to optimize the parameter, encode it in your circuit, you optimize it, and you do it until the thing converges. Yeah? This is very nice, and it's very appealing to physicists, yeah? Because physicists love variational stuff. They are already, from classical mechanics onwards, yeah? People love variational stuff. Yeah? The problem is that these algorithms are super expensive. Yeah? If you give a little budget to your students on AWS, they eat it up in an afternoon, yeah? Because it is very, very expensive. Yeah? A typical example, for instance, a variational quantum eigensolvers, yeah? And the same strategy as before. This is just a simple example where in every unit here, you calculate a component of the expectation value of the Hamiltonian, you bring it together, you define your cost function, and you do your, your iteration. Yeah? This is an explicit example where if you have your Hamiltonian decomposed in this way, the expectation value has this structure, and so on and so forth. Yeah? In order to train this variational quantum circuit, people came up with this parameter shift rules, yeah, where essentially, because your circuit has a parameter, you just vary the parameter and you calculate the partial derivative of the circuit in one go. Yeah? And that turned out to be a very useful trick. Yeah? Now, moving it to machine learning, you can have variation of this variational algorithm for supervised learning, for instance, yeah, where you have specifically the block that I mentioned before, where you need to prepare the state to embed the data. You have the circuit with the parameter, the measurement, and then you can calculate the expectation values, and so on and so forth. Yeah, this would be a typical example of a supervised learning variational algorithm. Yeah. Where am I? Yeah. Yes, in a deterministic fashion, because you calculate the expectation value. Yeah, you can do the same, by and reducing a number of the ensemble of the calculations, and get a probabilistic version where you just estimate conditional probability distributions. Yeah, that you can do as well. You can do versions of Born machine for unsupervised learning, but it's always the same story. Yeah, you have an initial state, something variational, some optimization loop, and so on and so forth. Yeah. And the same strategy applies, of course, if you want to extend it to deep learning, yeah, neural networks. Yeah, if you have many layers, the idea is here again you have your encoding block in green, and then you can have a mix of fixed gate and parameterized gate that you then try to optimize, and so on and so forth. And as I mentioned a few times, yeah. These operations are all very nice and elegant, yeah, but very time-consuming in terms of use of QPUs and in terms of budgets. Yeah, they can be very costly. Yeah. So we tried recently to find a quantum version of convolutional neural networks. Yeah? We are still in the kind of the variational realm, but we try to do something a little bit different. Yeah? Classical, they're very popular because that's a standard kind of setup that you use to classify, for instance, images of cats and dogs. Yeah? And the idea is always the same, that you have a few layers where you do convolutions, and you have a layer where you do the pooling, where you sort of reduce the dimensionality, and you keep doing it until you have only kind of the binary choice between cat and dogs, yeah? in this example. Yeah? The same you can do quantum layer, yeah? And that was done already 5 years ago. Yeah? You can have the quantum version of this. Yeah? Again, with convolutional layers, like here, where you see these unitaries are all mix everything up. That's the convolution. Then you have the pooling layer, where you see already that because of measurements, you manage to reduce the number of unitary in the system, followed again by convolution, pooling, and again the measurement at the end to decide whether your image is a cat or a dog. Yeah? And that's all good and fine. Yeah? But we tried to optimize this. And we started first by using these convolutional neural networks to classify music genres. Yeah? and here you see the setup that we had with the convolutional layer, the pooling layer, convolution, pooling, and then you decide whether it was rock or pop or something like that. Yeah? And it seemed to work very well. Yeah? And that led to the question, these are parameterized quantum circuits, yeah? And we of course want to optimize them. Yeah? You want to have less depth, less gates, make them more manageable. Yeah. So how do you find a circuit that captures what you want, but is not as complicated as you would naively write down? Yeah. Sorry, do you have the reference? And Matt, who is a PhD student, came up with something very, very clever. Yeah? And he proposed that by starting with kind of building blocks, yeah, of little circuits for just 2 qubits, yeah? He could then optimize with genetic algorithms the convolutional and the pooling operations by putting them together so that the circuit does what you want it to do. Yeah? It's a little bit technical, but it's a way of optimizing the circuit automatically without having to do much by hand. Yeah? And he applied it, for instance, to problems of quantum phase recognition. Yeah? And he studied here standard Hamiltonian with phase transition and using, you see, these fairly simple architectures that now has only 11 parameters. Yeah? Originally, in the paper that started the convolutional quantum neural network business, they had more than 1,000 parameters. Yeah? But by optimizing the circuit, you can reduce it to 9 and making it more manageable. Yeah? And it really manages to reproduce correctly the separation of paramagnetic, ferromagnetic, antiferromagnetic phases in the phase diagram. Yeah? So that was very nice. Yeah? And the code is an open source package now called Hierarchical. So if you go to GitHub, you're welcome to download and use it. Some other students are busy building up here a kind of a library of examples and tutorials to make it more accessible. Yeah? And another, in South Africa, we are very lucky that the biggest physics experiment that we have is the square kilometer array. Yeah? At the moment, it's just Meerkat, which is the one step towards the square kilometer array. So there are lots of data produced by the SKA. Yeah, and we try to play with pulsar data collected by the by the SKA and just try to classify it's a pulsar or not. Yeah, and we used the quantum convolutional neural networks from the software package that I showed. Yeah, and Donovan is the student that did this and has been just accepted for publication last week. So that should be published soon. Yeah, and he showed indeed that the data sets are not huge, yeah, are just order, I don't know, between 1,000 and 10,000 data points with a few levels, which is still manageable. Yeah, and he was able to show that these convolutional neural networks do a better job than the quantum version of support vector machines to classify pool. Of course, you can classify them on your laptop using classical machine learning as well. Yeah, but this was interesting to play around with it. Yeah. Another, probably still have another few minutes. Another very interesting thing that another PhD student of mine, Amy, is doing now is the following. Yeah, we want to see whether we can use this quantum convolutional neural network strategy to reinvent known quantum algorithms. Yeah, so you want the quantum machine learning algorithm to learn the algorithm. Yeah, and so you want to see if the machine using, you see, the same strategy of the convolutional neural network, where you have blocks that are cyclic, blocks that look more like pivots, and so on and so forth. This is just a simple quantum adder, I think this is. Yeah? And you see that, there are structures in this algorithm. Yeah? And you want to see whether a quantum machine learning can learn these structures. Yeah? And the idea was to couple these quantum convolutional neural networks with genetic algorithms. Yeah? So you start with something like this. Yeah? This would be here one of these pivot blocks. Yeah? And in the next generation, you could have, again, something like this, or it could change the order, or it could transform into something cyclic, and so on and so forth. Yeah? And sorry, this doesn't work now, because this was a GIF, but I think in the translation from Keynote to PDF, it got lost. But the idea of the GIF was to show you how the genetic algorithm invents or rediscovers the quantum Fourier transform algorithm. Yeah? And essentially, you read, this is the genetic algorithm from top to bottom. Yeah? And the GIF was repeating all these gray blocks, but you have it here. The result is this one here. Yeah? So this is just that you start, after a few iterations, you see the quality. Sorry, do I have it here? No, I don't have it here. The fitness parameter, yeah, was quite, oops, sorry, wrong direction. Yeah, the fitness parameter is quite slow. As the genetic algorithm improves, the fitness improves, and at the end, you have really the quantum Fourier transform for 4 qubits. Yeah? What is interesting is, you see here, the algorithm finds Hadamard. Yeah? We all know Hadamard is 1. Yeah? But up to triviality of that kind, it rediscovered the quantum Fourier transform algorithm. Yeah? And the same you can do for Deutsch, for Grover, and so on and so forth. Yeah? And we were hoping to have it in the archive before I come here, but it probably will happen a little bit later. Yeah? The other thing, at the beginning I mentioned that instead of going physics plus information, you can also go biology plus information. Yeah? And I mentioned a few times, sorry, how much time do I still have? 5 minutes, 10 minutes? Okay, 10 minutes. Yeah, that variational algorithm are very expensive. Yeah, so it's really important to start thinking about other things. Yeah, and biology tells us that the neurons that we have in our brain sort of spike. Yeah, there is a always when they communicate, there is a building up of current, and all of a sudden it spikes. Yeah, and the and the standard model, yeah, are these leaky integrate and fire neurons. Yeah, and it's a simple model. Yeah, and so you have the spikes. They're converted into potential, which is integrated until they reach a threshold, and then the spike is fired. Yeah, and this is coupled with a leaky, noisy part, yeah, which sort of models the natural environmental influences in the brain. And that sounds like it's good for noisy computers, yeah, because there is already a classical algorithm that uses noise to work. Yeah, so maybe we can do a quantum version of the leaky, integrated, and fire neurons. Yeah, and in fact you can do that. Yeah, and this we just put on the archive a few days ago. Yeah, you can model the spikes as rotation. Yeah, the leaks are the noise in your quantum computer that is there anyway. Yeah, and the big advantage of this is that you see, as you integrate it in time, like you see here, the rotations, the spikes, and so on and so forth, it has the same structure. So you can reduce it essentially to one qubit, yeah, that you keep measuring and re-inputting and iterating. So it's really very, very simple. Yeah. And now you can, okay, these are just the function that we use for the quantum simulation. Yeah, you can bring some of these modeled neurons together in a neural network, and you can try to let it learn MNIST and things like that. Yeah? And these quantum spiking neural networks, or here the quantum convolutional spiking neural network, if you compare the accuracy with others, yeah, you see that they are really competitive. Yeah, they really do really very well, and they cost much less. Yeah, they really cost much less. So that there is hope that maybe one can come up with different approaches to this kind of business. Yeah, let me use the last 2 minutes or 3 to discuss what to expect in the future, where the challenges are. Yeah, you know, I mentioned supremacy. Yeah, if you read the title of these papers of Google, IBM, and so on and so forth. Yeah, they started with supremacy. Then they started having advantage in the title. Some have now practicality in the title, others have utility in the title. Yeah? So the expectation kept going lower and lower. Yeah? And so, but let's see how let's focus on practicality. Yeah, and this is the word used by Microsoft. Yeah, they really want to find meaningful applications that we can be solved faster on the computers that we have now. Yeah, to show that you know, all the investments in quantum computing have already now some effect. And Matthias Streuer and his 2 colleagues wrote some time ago. Sorry, I don't remember. Probably last year or something like that. A very interesting paper where they compare an ideal quantum computer that we don't have yet. Yeah. 10,000 error-corrected logical qubits, yeah, with other nice parameters that we don't have yet, yeah, with what you can do today on a beta NVIDIA GPU. Yeah, investment, let's say $10,000, yeah, maybe less by now. Yeah, yeah? And they analyze the stumbling block, yeah, and the bottleneck is the input and output bandwidth, yeah, because even with the very idealistic parameters of this quantum computer that we don't have yet, yeah, the difference is a factor 10,000. Yeah, the GPU can read an output at 10,000 gigabits per second. Yeah? The quantum computer is many powers of 10 slower. Yeah, So that even if you the core of your algorithm is faster, if it takes you 2 weeks to input the data, yeah, it's not so good. Yeah? And, and their conclusion is that at the moment, yeah, the quantum computers that we have now, and maybe let's say in the next 1 or 2 PhD student generations, yeah, will be mainly good for big compute problems, yeah, that have small data, yeah, and not big data problems. Yeah. That, of course, doesn't mean that tomorrow one of you wakes up and know how to solve the problem. Yeah? And that's why we're all here. Yeah? So that the problems with where noisy quantum computers will be successful are really those that solve small data problems with exponential speed up. Yeah? In their paper, they really show the example of Grover. Grover is quadratic speed up. Yeah? So within their aim was to show that if you give the quantum computers a 2-week time frame, yeah, will it be able to beat a classical computer? Yeah? And quadratic speed up is not enough. Yeah? Quadratic speed up, you really need exponential speed up. Yeah? With the parameters of this ideal quantum computer that we don't have. Yeah? So we really need to focus on problems where where data are not too big. Yeah, if we want to show practicality. Yeah, if you are interested in solving the problem of data, then that's another story, and we should do that. Yeah. I was involved for a few years ago with GESDA, which is a Geneva Science and Diplomacy Anticipator institution. Yeah? And the idea was to find what problems should we address. Yeah? And typical problems that fall in this category of small parameters, small data, and big compute are carbon, for instance, finding new materials for carbon capture, yeah? Or tackling the problem of antibiotics in wastewater, yeah? Fertilizer production. Yeah? Bacteria can do fertilizers very cheap for free. Yeah? If you produce them industrially, it's very expensive. Yeah? So, but we don't know how bacteria does it. Yeah? Or, let's hope that we won't have to live through another pandemic. Yeah? But optimizing vaccine distribution is and so on and so forth. Yeah? And this is also a very interesting problem. Yeah? Sustainable food production, yeah? Because this is a problem coupled, for instance, to climate change, as different crops will not grow anymore where they're used to grow. Yeah, you have the problem of what crops will you grow there, and how do you import the food that you can't produce anymore locally? Yeah, because they want people to have their balanced amount of calorie and every day. Yeah, so it's really a very complicated problem, and and with a colleague in Switzerland, we are trying to do a quantum model to address this for data here from Bangladesh. But anyway, okay, so this was some random thoughts about quantum computing in the next few years. Yeah? And I hope it was not too depressing because of the critical comments on quantum machine learning, but it took us also a while to understand it. Yeah? But it's not depressing, it's a challenge. Yeah? Once you know where the problem is, you need to. And I know that some people in Brazil, like Ade Newton, I don't know if he's here. Yeah, he did some. Okay, he did some interesting work on optimizing the state preparation for quantum computers. Yeah, so there is hope. Yeah, thank you very much.
Thank you, Professor Francesco. Nice talk. Thank you, Professor. We have time for a few questions, please. Who?
Hi. I have a question about the part of nonlinear functions. In machine learning, normally you show the deep quantum algorithms, and we have multiple layers. But in classical machine learning, after each layer, we have a nonlinear layer, and quantum mechanics is actually by the fundamentally linear. And do you know some method of I know it's a very difficult thing in quantum mechanics, but do you know some applications or some methods to insert this nonlinear part in these after each layer?
You know, the nonlinearity is essentially your measurement. Yeah, you see here, the yellow.
Okay, but
the
it's
nonlinear.
just one application
Yes.
of a nonlinear
Yes.
function.
All the rest is linear. All the rest is linear. Yeah.
Okay, but there is there some way of putting these more nonlinear activation functions after, for example, as I have said, normally in deep learning we have multiple applications of nonlinear.
Yeah, no, in the standard approach, the nonlinearity comes at the end. All the rest is linear. Yeah?
Okay.
All the rest is linear.
Okay.
Yeah.
Okay.
You know, if you make it nonlinear, then it's no longer unitary.
Okay.
Yeah?
Okay.
You could, for instance, if you do it in a dissipative way, yeah?
Okay.
Then you could have a nonlinear kind of
You put some
Hamiltonian,
parts of you open the system in some
Yes,
places
yeah,
to allow these nonlinear effects to take place.
but then it's
in
no
the-
longer
Okay,
a unitary
okay,
quantum
okay,
computer.
okay.
Then it's something else. Yeah,
Okay.
yeah,
Thank you.
Yeah. Thank you.
There is another question.
Probably you give a lot of advice there in South Africa, because I know that you have a lot of administrative work there. You are director of an institute, and so probably the government is interested on your advices about what you have to do in quantum computing for the next years. South Africa and Brazil maybe are in a similar situation. So you have asked at some point that whether we are building a quantum computing. So this is a tricky question because there are physics groups building some superconducting qubits there, but is it a quantum computer? Or a quantum computer seems to be something larger, like you have also controls and software, and you put that in the cloud, and then people are going to use everywhere. And here in Brazil, we didn't reach this kind of integration. And at some point, you have showed 3 areas in quantum communication, quantum computing, and sensing. So what are usually the advices that you give there when some government people search for you for advice? How much, if you have a limited budget, how you are going to split your budget between those areas? Should you build necessarily a quantum computer or not? What are more important now for countries like Brazil and South Africa at this moment?
This is a very interesting question, and it occupied me for a long time, and I'm slowly changing my mind. But I will tell you what my thoughts are. Yeah? When we wrote the quantum technology roadmap, we intentionally said we don't want to build our quantum computer. We have also in South Africa groups working with squids, group working with ion traps, groups working with cold atoms. Yeah? But those are just experimental things. None of those groups has the ability and the funding to think of doing 1,000 logical qubits. That's beyond their reach. And I don't know what the budgets are in Brazil, but in South Africa, most of our science budget goes into the SKA. Yeah? So we wouldn't even have the money to do that at the moment. Yeah? And that's why we said we use quantum computers in the cloud, we focus on algorithms, and that's good. Yeah? But there is a but, because recently I read that countries like the UK and the US are thinking about export restrictions on quantum computers. Yeah? And the reason is that one of the things that quantum computers are good at is factoring. Yeah? And that's a threat to the secure communication kind of business. Yeah? So if one day they decide countries like ours can't import or use their quantum computers in the cloud, then, then we have a problem. Yeah? Then we have a big problem. Yeah? So I don't know. Yeah? One strategy could be that countries like South Africa and Brazil join forces, yeah, and say, okay, in Brazil we do the electronics, in South Africa we do the squids or the software or the other way around, and develop something. Yeah, it's probably the thing that we should think about. Yeah, because it's risky. Computers in the cloud. There are elections in the US in a few months. If they go the wrong way, yeah, they could decide we don't allow access to quantum computers to this country, and we are in BRICS, so we are allied with some fancy or not so fancy characters, yeah, that not everybody might like. Yeah? So it's really a strategic decision. Yeah? The same is for quantum communication. Yeah? We need to invest in developing our QKD systems, yeah? Because the same will apply there. Yeah?
Yes. Maybe the first letter is Brazil, B, South Africa, S, the beginning, the end, put together.
Yeah.
And go ahead.
That's probably the way to go.
No wait for United States.
No, that's probably the way to go.
Yes,
but
yes,
the advantage of communication and
But
sensing, that's much cheaper.
join force.
That you can really do. Yeah. But for the hardware of quantum then we probably need to join forces and be very clever about the technology that we choose, because you don't want to put all your hopes in the wrong technology. Yeah. So maybe the timing is almost right. The moment one knows which technology wins, one should jump. Yeah.
There is another question here.
Okay, thank you for your very nice talk. This is a trick question. If you had
the previous one was tricky enough.
Yeah. If you had to choose just one problem to invest all your efforts to achieve quantum practicality, which one would be this problem?
You mean hardware-wise?
No, even theoretically. Okay, you are studying quantum machine learning, okay, but a specific problem.
Yeah, no, simulations of quantum systems. Yeah, finding new materials or chemical reactions, application for the pharmaceutical industry. Yeah, those kind of problems probably. Yeah, and in all of this, I never mentioned other architectures. Yeah, like those quantum annealers. Yeah. Because those are also machines that are good at solving a specific problem, yeah, and people use them already with advantage, yeah. But it's not a fancy universal quantum computer, yeah, like D-Wave, yeah. People can use them to solve optimization problems quite efficiently, yeah.
But you think that quantum advantage, even by D-Wave, is already got? I mean,
if you listen to the companies, they're already there. Yeah. But at least people use them to solve problems. Yeah?
Yeah, but
Yeah.
okay, I already tried a lot of times solve the problem with the wave, but I didn't get advantage. I mean, the
but-
company mentioned that they already
know,
got
I know.
that. Yeah.
Yeah, no, I don't know. It's maybe they will reach sooner an advantage for a specific category of problems than others. But I think it's really time that people come up with quantum advantage, because otherwise the whole hype of quantum computing will be a little bit in trouble. Yeah.
There are a lot of questions from the Google, the internet.
Oh, okay.
And
okay.
take one, just
Please.
one. I don't know who sent, but this: which hardware is the best one to run the QML algorithm? This is the question.
I don't know. I don't know. It's very challenging. One, because, for instance, I know I met a gentleman from IBM. Yeah, at the moment, the only quantum computing hardware we have access to are IBM machines, because of an agreement between South Africa and IBM. Yeah? So I don't have any personal experience on any other hardware. Yeah? So I can tell you. Yeah?
Okay, Professor, one last question, if you want.
Hello. Do you guess that some kind of algorithms that worked relatively well in the current NISQ era will become less or more important if we achieve supremacy?
Yeah, I mean, for a long time, people had big hopes on these variational algorithms, but they turn out to be just too expensive. Yeah, you can't really use them for those purposes. Yeah, so if I were a young PhD student, I would try to look into alternatives to variational algorithms. Yeah? That run on noisy intermediate state quantum computers. Yeah? That's what I would do. Yeah? And try to come up with something else. Yeah? The variational, I mentioned it in passing. Yeah? It's quantum computing is driven by physicists so far. Now more and more computer scientists are coming in, so things will change. Yeah? And physicists all grew up on variational stuff. That's why at the moment they see something variational, they're happy. Yeah? But the hardware is not so happy because it's just too expensive. Yeah? But there are many people that are working on improving that. Yeah?
Okay, thank you very much.
Thank you very much,
Francesco.
Thank you.
Bem, antes da gente sair para o coffee break, deixa eu dar alguns avisos, bem rapidinho, né? A SBMAC, a Sociedade Brasileira de Matemática Aplicada à Computação, nos enviou alguns livros, né, com títulos pertinentes ao nosso encontro. Então, no final de cada plenária, será sorteado, né, um livro para os participantes do evento. E o primeiro livro que vai ser sorteado agora é o livro Algoritmos Quânticos de Busca, do professor Renato